Hi, my name is Shahnawaz. In this lecture, we are going to study some operations on modules. So we have seen in rings. So if we have a ring A and suppose I and J are two ideals in ring A, then A, since we had two operations on A, i.e. the addition and the multiplication, so we can define the product of ij, and if we define this product to be the finite sums of product of elements of I and j, so it is I times j, where this I is in I and j is in j, then this set has the ideal structure. Now since if we consider an A module, say M is over A module, where A is a ring, then it is natural to ask, in this case we do not have the internal multiplication in the modules. However, we have the scalar multiplications. We have a function from A cross M to M, so it is natural to ask if S is any subset of A, then can we define some structure on the set SM. So now if we take, say if we have M1 and M2 in M, then the product M1 and M2, this won't make any sense because we don't have the internal multiplication in modules. However, if A is an element of A and M is an element of M, then this element makes sense. So this element is also an element of M. So it is natural to ask, can we give this set SM some structure? First of all, let us define this SM. So if we define SM like this, so if we say it consists elements like this, S times M, where S is in S and M is in M, then M is an element of M, then this set is just a set. It does not have any structure. However, if we define the same set like this, let us define this to be the finite sum, say it is Si Mi, where this I runs from 1 to n, where this Si is in S and Mi is in M. Then this S being a subset of A, then SM is contained in M, because this M is closed under the multiplication by the elements of A. So this is a subset of A. Now it is natural to ask whether this set SM is a submodule of M or not, and it is easy to verify that this SM is actually a submodule of M. It is a submodule of M, because M is given to be an A module. Now let us look at this set. Suppose we have I to be the ideal generated by the elements of S, i.e. this I consists of the elements of the form, so it has elements of the form, say alpha I and Si, where this I runs from 1 to n, where this alpha I is in A and Si is in S. That is, I is the ideal generated by the elements of S. Then it is natural to ask what is the relation between the submodule SM and IM. Now S being the generating set of I, so Si is contained in I. So the one inclusion is trivial, because S is contained in I implies Sm is contained in Im. So this inclusion is trivial. Now the question is whether this inclusion is true or not. So let us consider some element in Im. So let x belongs to Im. Then this x is a finite sum of the product of elements of I and m. So in this x is here some element, say let us take this is ai and mi, where I runs from 1 to n, and this ai, this is element of I. But I being the ideal generated by the elements of S, then this ai is actually equal to this is actually equal to sigma say alpha, say j runs from 1 to m, so it is alpha ij sj, where alpha ij is in A and sj is in and sj is in S. Now let us now look what the element x in Im look like. So this x is then equaled, so this is sigma I goes from 1 to n. Now this ai, this we can replace this ai with this expression over here. So this is sum j runs from 1 to n alpha ij sj and mi. Now note that A is commutative ring and there is no concept of left A or right A modules, so we can commute these elements. So this is same as sigma, so this is some m here, so this is sigma I goes from 1 to n, sigma j goes from 1 to m, and this is sj times alpha ij mi. Now alpha ij being an element of A and mi being an element of m, and we know that am is same as m because this m is closed by the multiplication with I mean this m is closed or the scalar multiplication by the elements in A. So this is an element of m and sj is element of S. So this expression over here, this is actually an element in Sm. So this x was chosen in Im, so we ended up in Sm. So that means this inclusion over here is also true. So this means that if we look at the submodule of M, so if S is contained in A, then Sm is a submodule of M. And if I look at the ideal generated by the elements of S and I look at this product Im, then these two sets are equal. So we'll often use this notation. So in place of Sm we write Im, where I is the ideal generated by the elements of S. However, if sometimes this S may be singleton, say it is just suppose it contains the element X, then this it is good to write this Im, where this I is ideal generated by X by the expression Xm. So if this S is singleton, then in place of Im we write maxm. So this was about the product. Now in case of ideals, we also have the notion of quotient ideal, I mean the columns. So if I and j are two ideals in a ring A, then we have seen that the I colon j is actually an ideal in A, where this I colon j was defined to be all those elements in A such that aj is contained in I. Now there is this question, can we have this notion of colon in modules? So let us suppose we have two A modules. So let m and n, say these are two A modules. Now there is this question, can we have the notion of their colon? Now this answer comes from, the answer of this question comes from this definition over here. So if S is the singleton set, then the submodule Sm is same as Xm. So if we define this set to be all those elements in A such that A n is contained in M. Now note that this is actually a subset of A. Now it is natural to ask whether this is an ideal of A or not. So indeed this is an ideal in A, because one can look over here. So this set over here, this contains 0, because 0, which is equal to 0 times n, is contained in M. So this 0 is an element of M. So if we have two elements, say A and B in M colon n, then what can we say about their sum? I mean, whether the sum of these two elements is in M colon n or not. So if we look at if we look at the sum of A plus B times an element of n, so this is actually equal to an plus bn for all n in n. Now because n is an A module, so this follows by the definition of n, by the definition of n being a module. Now A being an element of M means A and B being the element of this column means an is contained in M and bn is contained in M. So this means here that an is an element of M and bn is an element of M. So that means this is an element of M for all n in n. So this would imply that A plus B times n is contained in M. So this means this column over here, this is closed under addition. Now let us check whether this is closed under the scalar multiplication or not. So let x be an element of M colon n and A be an element of A. Now we have to check whether this set over here is closed under the multiplication or not. We have to check whether this is an ideal of A or not. So I have used the term scalar multiplication, but that is not true, because we are going to see whether this set over here is an ideal in A or not. So we have to simply check whether this set is closed under the multiplication of elements from A. So let us look at this element A, x. Now x being an element of M colon n, so this would imply that x times n is a subset of M. So we have to check whether Ax is a subset of I mean ax is an element here or not. So this would imply, so if we look at this element here, so this is same as a of x times n for all n in n. Now xn being a subset of m, this would imply x times n is in m for all n in n. So this means that this element over here, this is an element of a n, but n being an a module, a n is simply equal n. Sorry, I did a mistake. So xn is an element of m, so this is an element of am. Now m being an a module, am is actually equal to m, so this is an element of m. This means this column over here, this is also closed under multiplication. So this means that this column over here, this is an ideal in A. Now let us suppose that this m is actually the id I mean this module m over here, this is a 0 module. Then if we look at this column over here, then this will be the set of all elements in A such that a times n is contained in 0. This is the set of all elements in A such that a times small n is 0, where this n is in n. So since we have defined the annihilator of a module, so this is actually the annihilator of this a module n. Now suppose we are given an a module, so m is over a module and n is also, so n is a sub module of m. Then this quotient m mod n has a natural a module structure, so this is also an a module. Now there is this question that suppose A is a ring and I is an ideal in A. So the question is, can, so this is our hypothesis, A is a ring and I is an ideal in A. So suppose M is an A module. Now the question is, can we give M an A mod I module structure? I mean this can this structure be natural? Otherwise we can define the scalar multiplication by the elements of A mod I with the elements of M, given as that if we take an element A bar here and multiply with M here, so if we define this product to be the 0 of this M, then this is obviously well defined operation, but this is not natural. So I mean, is there any operation? So if I take an element A bar in M and an element M in M, can we define like this AM, where A is in A. But this operation is not well defined, because if we take two representatives of A bar, then suppose A and B bar, I mean B, suppose B is an element in the equivalence class of A, I mean A bar and B bar are same, then this B bar times M is BM. So A bar and B bar are equal, but we cannot say whether A and B are equal, so A and B may not be equal. So in that case, this operation over here, this may not be well defined. But so what I mean these two elements to be equal. So AM must be equal to BM, where A and B are in the same equivalence class of A. So for all A and B, for all n b, so this would imply A minus B times M must be equal to 0. So this would imply that A minus B should be in the, so this M is in M, note that this M is in M. So A minus B times M is 0 only if A minus B is in the annihilator of M. So that means we can give this M the A mod I module structure only if this I has I mean this I so we can give M the A mod I module structure only when this I is contained in the annihilator of M. In that case, if we take any two representatives of this A bar, this will give us AM, which is 0, and this will give us BM, which is again 0. Then in that case, this M has the natural A mod I module structure.